Computers can do that?
Before we start talking about the distance formula, let's remind ourselves how we actually plot points in a plane. Well, in a Cartesian plane, we have this coordinate grid made up of two axes, the x-axis and the y-axis. Whenever we have these axes, it's also important to include a scale. So I'm going to say that each of my boxes is equivalent to 1 square unit. Another way of labeling that is I could actually mark off each of these lines being 1 unit, but that's going to get a little crowded. So what I'm going to do instead is mark every 5 boxes. 1, 2, 3, 4, 5 to the right. 1, 2, 3, 4, 5 to the left, and recall that to distinguish our 5 to the right and 5 to the left, we'll use a negative, because a negative is simply a sign of direction, meaning left in this case. I'll go 1, 2, 3, 4, 5 up, and 1, 2, 3, 4, 5 down. And upwards is positive, and downwards is negative. Now, when I read off coordinates from a point, recall that points are always written with the x-coordinate first and the y-coordinate second. So that when I go to plot these points, point A will be 2 units to the right in the x direction and 4 units up in the y direction. A. Point B is 3 units left in the x direction and 2 units down in the y direction. Point C has gone no units in the x direction and up 5 units in the y direction. And point D has gone right 4 units in the x direction and no units in the y direction. So I'll go right 4 units and up no units. So now that we've reminded ourselves how we plot points in a coordinate plane, let's see how we can actually calculate the distances between a set of given points. So on a fresh set of axes, let's plot the points P, Q, and R. I'm going to use the same scale, which is 1 box is 1 square unit, so that each of these line marks is 1 unit. So my first point P is back 1 unit in the x and up 1 unit in the y, which will put me there. My point Q is right 2 units and up 1 unit. And my point R is right 2 units and up 5 units. Okay. So now I'm going to find the 3 lengths PQ, QR, and PR. Well, segment PQ is this segment, and it's pretty easy to count off its length. It's gone over 1, 2, 3 units, so its length will be 3. Segment QR is similarly easy to find. It's gone up from Q to R 1, 2, 3, 4 units. Unfortunately, segment PR is a little bit trickier to find because there isn't easy to count units in each of these situations. But recall that each of these is a square box, meaning that this corner angle is a right angle. I know that segment PQ is 3 and segment QR is 4. And since these sides form a right triangle with hypotenuse PR, I could use the Pythagorean theorem to figure out the length of PR. So PR squared would be equal to 3 squared plus 4 squared. So that PR will be the square root of 9 plus 16, which is the square root of 25, or just 5. This Pythagorean theorem concept, while it's easy to understand, isn't always the quickest and most effective way to find the distance between the 2 points. For that reason, mathematicians derived the distance formula. Given any 2 points with coordinates x1, y1, and x2, y2 respectively, the distance between these 2 points is the square root of the first coordinate minus the second x coordinate squared, plus the first y coordinate minus the second y coordinate squared. Now, this is a really complicated thing to try to remember. So we have a little notation that helps us represent the difference in x's. We don't want to use the letter d because sometimes we use the letter d to represent distance, so we'll use the Greek letter d, or delta, and call this the change in x. We'll do a similar way of representing the change in y, or difference in y, with a delta y. So that a simpler version of our distance formula is the difference in x's squared plus the difference in y squared. Now this difference is sometimes also referred to as the change in x, or difference. So the difference in something is just how much it has changed. So let's see how we can use this in an example. Here I have 2 points, and rather than graphing and calculating their distance, I'm going to apply the distance formula. So I'm going to use my easier to understand distance formula, which is with my deltas, or differences in. So to apply that formula and find the distance between these 2 points, my distance will be the square root of the change in x. Now notice from -4 to 2, x has increased by 6 units, so my change in x is 6. And I'll also need my change in y. Now from 7 to 8, my y value has increased by 1. So I end up with the change in x squared, which is 6 squared, plus the change in y squared, which is 1 squared. So that the distance between these two values is 36 plus 1, square rooted, or the square root of 37. In my second example, I'll calculate its distance. Again, I'll need my change in y and change in x. My change in x from 0 to 3 has gone up 3 units. So that will be 3 squared plus my change in y from 0 to -3 has gone down 3 units. So I'll write that as -3 squared, which will be the square root of 3 squared is 9, plus -3 squared is also positive 9, because a negative times a negative is positive. So this gives me the square root of 18, which simplifies to 3 rad 2. So this distance formula can save us a lot of time as opposed to graphing and using Pythagorean theorem. Now, we will actually derive this distance formula in class tomorrow to see where it actually came from.